In this video, we're going to look at infinite sets and some things that you can learn about infinity when you look at infinite sets. If you're not comfortable with the basics of set theory, then go check out my other video titled Set Theory Basics. So let's take a look at two different sets. One, the set of all English words, and two, the set of all possible letter combinations. And we're going to ask the question, are either of these or are both of them infinite? Well, the first thing that we can say is that S1 is a subset of S2 because all English words have to be combinations of letters, and it's a proper subset because there are letter combinations that are not English words. Let's start off by asking if S1 is infinite. Well, think about your average English dictionary. Does it go on forever? No, it's finite. And even if you say, well, there are some words that are in some dictionaries and not in other English dictionaries, well, the union of all of those finite sets, those dictionaries, are still going to be finite. So the union of multiple finite sets is still finite. Next, let's look at S2 and see if we can figure out whether it's infinite or not. Let's start by assuming the opposite, assuming that it's finite. And if it's finite, then we can say there's some element E, which is an element of S2, which is the longest string of letters. All other elements in S2 are shorter than E, or equal to the length E. But since we could take E and then just add another letter to the end of it, say we add an S to the end, well, now we've generated a letter combination that is longer than E, but also belongs in S2. Then we can also add another character to this new element, and we can keep doing this, so you cannot have a longest element of S2, therefore it has to be infinite. For the rest of the video, the infinite sets that we're going to be dealing with are going to be the number classes. We're going to review them really quickly, but if you're not familiar with the number classes, I'm going to put a link to a Khan Academy video in the notes. The first number class is the whole numbers, and this set starts at 1 and then counts by 1 up to infinity. The natural numbers is very similar, only it starts at 0 and counts by 1 to infinity. The integers counts by 1 in both directions to infinity, so it starts at 0 and goes into the negative numbers to negative infinity, and in the positive numbers to positive infinity. Then you have the rational numbers, and these are all the numbers that can be represented as a fraction. So not only are you going to negative infinity and positive infinity, but every fraction in between integers is represented as well. And then you have the real numbers, which also include numbers that can't be represented in a fraction, like pi or other irrational numbers. Infinity crops up in all these sets, and as you can see, in the whole numbers, you're counting to infinity. In the natural numbers, you're also counting to infinity. Within integers, though, you have two infinities to deal with, positive and negative infinity. The rational numbers deal with positive and negative infinity, but there's also an infinite number of fractions in between each rational number. To add even more confusion, in real numbers, you've got positive infinity, negative infinity, all the numbers in between that are infinitely many here as well, but also the irrational numbers, their decimal representation goes on for infinity. So the question we want to ask are these sets the same size, or are they different sizes of infinity? You'll remember from the last video that we said the sizes of two sets are equal if there's a bijection between them. Quickly, I want to introduce some convenient notation when talking about set sizes, and that is just the straight bars. So if you have a set S1 and you put bars around it, you're just talking about the size of that set. So if we want to compare the size of the whole numbers to the natural numbers, we have to define a one-to-one mapping from one to the other, aka a bijection. Well, putting them next to each other, it's fairly obvious how to map. We can just map 1 to 0, 2 to 1, 3 to 2, and just keep going like this for infinity. So the mapping we're going to have is a function, f of x, and for every whole number that we pass into x, we're going to generate a natural number which is equal to x minus 1. And this is our bijection, so the size of the whole numbers is equivalent to the size of the natural numbers. Next, let's compare the sizes of the whole numbers to the integers. This time we're going to have to be a little more creative because with the integers we have two infinities, negative and positive infinity. But we can start off by mapping 1 from the whole numbers to 0 in the integers. And then let's take 2 and map it to negative 1. 3 could map to 1, 4 to negative 2, and 5 to positive 2. And we're starting to see a pattern of how we could map all of the numbers and the whole numbers to the integers. And just like we did for the natural numbers, we can define this as a function. So f of x in this case, equals -1 to the x minus 1 times the floor function of x divided by 2. And if you're curious, feel free to pause the video right now and plug some numbers into this function to make sure it is the bijection that we defined up top. Well, if we thought we had to be creative in coming up with a bijection from the whole numbers to the integers, it's going to take even more ingenuity to come up with a bijection to the rational numbers, because this time, not only are we dealing with positive and negative infinity, but we're dealing with infinities between numbers as well. If you have 0 and 1/2, there are an infinite number of numbers between them, like 1/3, 1/4, 1/5, 1/6, and so on. We can deal with all those infinities in the integers by breaking out the numerators here from the denominators here. So this will be a grid of fractions where the numerator comes from the column and the denominator comes from the row. So this cell would just be 1/1, or 1. This would be 2. This would be 3, 1/2, 2/2, 3/2. Oops. And then we have 1/3, 2/3, 3/3, and so on. We could keep filling this in to infinity in both directions. Now for our bijection, we'll start off by mapping 1 in the whole numbers to this cell, which is 1. Then we'll step to the right, and from here we'll follow the diagonal down, and then we've reached the end of the diagonal, so we'll go down, and then we'll follow the next diagonal up. And then we've reached the end of this diagonal, so we'll go right again, and then we'll follow this diagonal down. And we can keep going on like this forever, and we will have mapped all of the whole numbers onto all of the rational numbers, which is an amazing thing, because now we've just proven that the size of the set of the rational numbers is the same as the size of the set of the whole numbers. Now let's try to see if we can find a bijection from the whole numbers to the real numbers. So this time, not only do we have to worry about positive infinity, negative infinity, the infinity between every number, but we also have to worry about the infinity that's encapsulated by irrational numbers. Pi, for instance, is 3.14159 repeating on for infinity in a non-repeating way. So we're going to approach this by doing a proof by contradiction, which is similar to the kind that we used at the beginning of this video. So let's say we had some really clever bijection from the whole numbers over here to the real numbers over here. And this bijection goes on to infinity, but for convenience sake, we're just going to put all of the numbers between 3 and 4 at the beginning, because remember, if we come up with a bijection, the order doesn't matter. So we have this bijection, and we say that's the complete set. We've mapped all the numbers from the whole numbers to the real numbers. But since not only are we going on infinitely downward, all of these numbers go on infinitely to the right as well, we're going to run into a little problem. What if we took the number that started with a 3, like all of these do, but then in the first number, we take the first digit after the decimal, and we add 1 to it, make that a 2. We take this second number and take the second digit after the decimal and add 1 to it as well. And we keep doing this, and if we run into a 9, we'll just wrap it over to a 0. And we keep doing this all the way down this diagonal, and we keep going to infinity, both down and to the right. Well, now we've come up with a number that doesn't exist in our bijection, so the bijection can't exist because it can never be complete. So since a bijection from the whole numbers to the real numbers can never account for all of the real numbers, what we've shown here is that the size of the real numbers is greater than the size of the whole numbers, which so far, all of our other comparisons have shown that they actually are equal to those number classes. But this one, it does not hold. So we've just shown that there are different sizes of infinity, which is kind of crazy and definitely cool. Mathematicians use the Hebrew letter aleph to denote these different sizes of infinity with a different subscript. So we just showed that the size of the whole numbers is the same as the size of the natural numbers, which is the same as the size of the integers, which is the same as the size as the rational numbers, which is all equal to aleph with a subset of 0, which can be said aleph naught or aleph null. Then we showed that there was a bigger infinity, the size of the real numbers, and this is equal to aleph 1. The values of aleph 1 and aleph naught are related to each other by this equation. Can you figure out why? I'll give you a few hints. First, remember that the size of the power set of the set of natural numbers is equal to 2 to the size of the set of the natural numbers. Also, think back to the diagonal proof that we used to prove that the size of the set of whole numbers is not the same as the size of the set of the real numbers.